Some SN1 reactions give very unusual mixtures of products. An example could be a reaction which starts with this branched alkyl bromide, and when exposed to ethanol, two products can be isolated. One is the expected product, where bromine is simply replaced with ethanol. All the stereochemical information in this chiral center is lost, but that is expected. But oftentimes this reaction produces another product. Where not only the ethanol did not attach to the original carbon atom, but also the carbon skeleton itself appears to have changed. And this phenomenon is explained by the so-called carbocation rearrangements, which in principle occur whenever carbocations are present. SN1 reaction is just one of the many reactions that involves carbocationic intermediates, and it's our first example. But basically, anytime we see carbocations, we can expect some of these rearrangements. So let's see how these reactions actually proceed. Starting with this starting material, the first step is the loss of bromide to give us our cation. And if you look at this cation, you'll quickly realize that this is a secondary cation. And if we draw this hydrogen, what can happen is that the hydrogen moves onto this cationic center. This movement is very quick, and it's known under the term hydride shift, because hydrogen moves with its electron pair. Now we have CH2 here, but the original carbon where hydrogen was remains positive, since hydride moved as a hydride with hydrogen. And this is now a tertiary cation, which is more stable. Okay. These rearrangements are often driven by cation stability. So if we have a possibility for movement of a hydride, that will give us tertiary cation from a secondary or even better primary cation. These things will happen very quickly. Hydride also is not the only group that can move. Another thing that is very common is the metal shift. And I will give you an example which occurs in these neopentyl systems. And so if you think about this reaction, loss of bromide would generate the primary cation. But primary cations are very unstable. And so what happens in our example is that while bromide is leaving, methyl group simultaneously moves over here, and the primary cation is never even formed. And so we directly go into the tertiary cation. So this would be a concerted metal shift. So as a general rule, cationic intermediates can rearrange through either hydride or metal shifts. These shifts are typically going into the direction of more stable cation, so from secondary to tertiary, from primary to tertiary. In cases where our starting cation is semi-stable, such as secondary, we actually have two steps. First is the formation of secondary cation, then the rearrangement to form a tertiary one. In cases where the starting cation is relatively unstable, such as the primary one, these two steps are often concerted, so they occur simultaneously with each other to immediately give the tertiary product at the end. Let's see now the orbital picture just a little bit. If we look at our cation, this is a planar intermediate, and this p orbital is empty, and attached are the carbon, the metal group, and the hydrogen, and in its neighborhood are these sp3 hybridized substitution. The hydride moves over here simply by tilting over to the left, and then hydride shift gives us this hydrogen transfer, methyl group H, and now the left carbon, the right carbon, sorry, has this empty p orbital. So this is a very general rule. Whatever stable cation we can form will be formed through rearrangement. So this occurs for allylic cations as well, because allylic cations are stabilized by resonance. So if we expose this iodide to acetic acid, we will get a mixture of products. We will get the expected product and the rearranged product, where our acetic acid is now closer to double bond. And the mechanism that occurs is relatively straightforward. We get our initial secondary cation, and then hydride shift occurs to move the hydrogen over here and to give us a plus here. And this is a more stable allylic cation, which then gives us a product. Now, these two things, they look like resonance structures, but these are not resonance structures. If you think about one of the first requirements for drawing correct resonance structures is that atoms do not move, and here we have the movement of the entire atom, hydride. So this hydrogen atom moves, not only electrons. These are actually different cations, not just resonance structures of each other. So this is an important distinction to keep in mind. So with this, we completed our treatment of SN1 reaction. So to summarize it, it's a two-step nucleophilic substitution. The rate-limiting step is the decomposition of our starting material into a cation and leaving group. That's why nucleophile doesn't matter, because it's not involved in the rate-limiting step, but the structure of a substrate matters. Tertiary substrates work best, secondary substrates work so-so, primary and methyl not very likely. Since these reactions proceed for cationic intermediates, which are sp2 hybridized and therefore planar, two important things happen in these reactions. One is the loss of stereochemistry, racemization of your enantiomer pure starting materials, and the other one is rearrangement of carbocations, which often gives you different structures. These rearrangements are driven typically towards the more stable cation. In the final topic of this lecture, we will compare the features of SN1 and SN2 reactions and factors that facilitate